Okay, welcome to our Physics 2010, Chapter 5. We're going to be looking at circular motion and gravitation. So, prior to this lesson, we have looked at linear motion, linear velocity, and acceleration. And so, in this chapter, we're going to be looking at the differences that occur when an object travels in a circular path. So imagine we have a ball on a string and it's going to travel in this circular path here. The magnitude of the velocity, the straight line velocity here, the velocity 1, may not be changing in terms of its rate of speed, but because the direction of this ball is constantly changing, it keeps turning and turning more and more to make this circular path. The direction is changing, and since velocity is a vector and all vectors have both magnitude and direction, it means although this magnitude may be staying constant, the direction is changing, which means it is accelerating. But it's a different kind of acceleration than what we have been talking about so far when we've talked about motion in a linear sense. This type of acceleration we are going to denote with the subscript r, and it is called the centripetal acceleration. So as I said, the centripetal acceleration here is caused by the fact that the direction of our velocity here keeps changing. It keeps angling more and more to the right, and as that direction continues to change, it's causing a change in velocity. And a change in velocity with respect to time equals acceleration. In this particular case, we're specifically talking about the direction of the velocity changing, which leads to this centripetal acceleration, A sub r. And our formula for centripetal acceleration, which you're going to need to remember here, is velocity squared over r. So that's caused by the change in direction over time. Velocity squared over r. Okay, let's move on from that. And again, this term is centripetal. So we're talking about centripetal acceleration when you see the subscript r here. Another thing to note about the centripetal acceleration is its direction. Acceleration, just like velocity, is a vector, so it has magnitude and direction. And the centripetal acceleration is always pointing towards the center of the circular path. So as this direction of the velocity continues to change, here it's going in that direction, and then the direction changes to be pointing in this way. The centripetal acceleration always passes through the center of the circular path. So if we look at this formula here, v squared over r, the larger v gets, so if the velocity v gets bigger, then the centripetal acceleration will also get bigger. So greater speed equals a greater centripetal acceleration. But r is on the bottom of this ratio or fraction. So if r, the radius, gets much, much bigger, then the centripetal acceleration will be less. So something with a large radius, like the Earth, results in a relatively small centripetal acceleration. So some terms to talk about here when we discuss circular motion. First thing here is period. T in this case is representing period. T, I believe, is for time. I think that's where the abbreviation comes from, because it is a unit of time. Period is telling us how long does it take for this record, for instance, to go all the way around. Trace it here with my stylus. Goes all the way around back to the beginning. What was that time? How long did it take? So it's a unit of time and essentially just describes how long does it take for something to occur, for one complete rotation. The inverse of period is frequency. So frequency is how many times per second. And so frequency equals 1 over t, and t equals 1 over f. They are inversely related to each other. So if it takes 1 minute or 60 seconds to go all the way around, then the frequency would be 1 over 60. Now, velocity is equal to the distance over time. We know that from when we talked about linear velocity. And so what is the distance? If you were sitting right on the edge of this record and you went all the way around, what would the distance traveled be? Well, for a circle, the distance would be the circumference, which is equal to pi times d, which is the diameter, and diameter is 2 times the radius. So we can also describe that as 2 pi r. So if we take 2 pi r, the distance, or the circumference, divided by the amount of time taken to make the complete loop, the period, we can describe the velocity of a point on the edge of the circle traveling in a circular path. So velocity is 2 pi r over t. So that's a formula we're going to want to take note of. Okay, let's look at an example problem here. We have a tennis ball on the end of a string being spun around and around and around in a circular pattern. The ball has a mass of 50 grams and is revolving in a horizontal circle with a radius of 0.600 meters. It makes 2 revolutions in 1 second. So so if we have 2 revolutions in 1 second, then 1 revolution would be made in half a second. And so that is the period. For the amount of time taken to do 1 revolution is half second. So the period, t, is 0.500 seconds. What is the centripetal acceleration? So let's move on here to the next slide. The frequency is 2 revolutions per second. So as I said, that means that the period is the inverse of that, 1 over 2. So 1/2 or 0.500 seconds. The mass is given to us in grams. We typically want to convert everything to kilograms. That's the primary unit of mass that we want to use. So we're going to use 0.150 kilograms. We're just moving that decimal place 1, 2, 3 places. And in the problem statement, we were told that the radius of the circular path is 0.60 seconds. So we need to know, first of all, what is the velocity of the tennis ball? How fast is it traveling? Well, the distance traveled is the distance of the circular path, which is the circumference of the circle, 2 pi r, divided by the amount of time it takes, which is the period, t. So we have 2 times pi times 0.600 meters. That's the distance traveled. And the amount of time is 0.500 seconds. And so if we calculate that, we should get a velocity of 7.54 meters per second. Okay, so once we know the velocity, then we can find the centripetal acceleration. Centripetal acceleration is equal to velocity squared divided by r. The velocity is 7.54 meters per second. Don't forget to square that, and then divide by the radius, which is 0.600 meters. And so that should give us 94.7 meters per second squared. So that's the centripetal acceleration that is accelerating the ball towards the center of the circular path. So we learned earlier about Newton's second law of motion, that the sum of forces equals mass times acceleration. That still is true even when we're talking about centripetal acceleration. So Newton's second law of motion still applies. The sum of forces equals m times a sub r. But a sub r, the centripetal acceleration, is equal to m times v squared over r. I'm sorry, just v squared over r. So another way of writing Newton's second law of motion for circular motion is going to be equal to the sum of forces equals mv squared over r. We're going to want to keep that equation handy because that's going to be useful in some of the problems we do this chapter. So if the ball is accelerating towards the center of the circular path, and the ball does have mass, then we have mass times centripetal acceleration. So that means we have a force. That force is the tension in the string. So spinning a ball attached to a string around in a circle is one example of the force. We can the force here is the tension, but we don't necessarily need to have a string. Lots of objects travel in a circular path without strings. Planets might orbit the sun, or we'll find that that's actually an elliptical orbit, but it could, theoretically, planets could orbit the sun in a circular pattern, with gravity being the force here, or cars traveling in a circular pattern. The friction between the tires and the road are causing the force. Whatever the force might be, it is what keeps an object traveling in a circular pattern, and it is equal to m times the centripetal acceleration, which is again is equal to mv squared over r. One last thing before I wrap up this first video from Chapter 5 is just a conceptual thing. If our ball is traveling around and around in this circular path, and the string were suddenly cut, if we somehow could just stop this force, it's keeping it on its path. Some people might be under the false impression that the ball flies outward, or maybe even straight out from the center of rotation. And that does not happen. The ball would take off in a straight line that is tangent to the circle here. So you can see that here from the sparks. They are flying off tangent to the circle, perpendicular to the radius. I'm going to stop the video here. I'm limited to 15 minutes, and I'll resume with the next video.